Hello, welcome to another module in this massive open online course. So, in this module, let us look at another class of problems or another class of optimization problems specifically pertaining to linear modeling and approximation, which arise very frequently in various applications across both engineering, science and so on. So, this is a very important class of problems. This is termed as linear, wherever you have models, and typically most of them or frequently they are modeled as linear models. So, we have linear modeling and approximation problems. Linear modeling and approximation problems, and what you can see in this is that if you consider the linear model, a general linear model can be described as follows. Consider the linear model y bar equals a x bar, where we have A, this is in general an m cross n matrix, and which implies of course that if x is a vector, x is an n cross 1 vector, and y bar is naturally an m cross 1 vector. Now, what we assume, or typically in this model, this vector x bar is unknown, which has to be determined. So, x bar is unknown and it has to be determined. So, x bar is to be determined, and now frequently what you have also in such a system, now of course, let us start by considering a simple example. Let us say A is a square matrix, okay, that is M is equal to N, okay. If M is the number of rows, N is the number of columns of A. Let us now, if you look at this system, you can see what is M in this system. M is basically the number of equations, it is the dimension of Y. So, M equals number of equations. And n equals the number of unknowns. Okay. Now, what happens in this is that let us assume a simple scenario to begin with. If m equals n, and this everyone would know, m equals n and A is invertible, it's if A equals m and A is invertible. Remember, this is has to be given. Now, this implies I can find y bar equals a x bar, I can determine x hat or the estimate of x equals A inverse y bar. Okay. This I think is the typical solution for the linear system, which most people would know or most students would know. Now, however, frequently what we have is that you have this y bar is, well, it is not exactly equal to A x bar, it is actually A x bar plus n, where n is the noise. So, I write it as y bar equal, this is the linear model, y bar equals A x bar, and A is your m cross n matrix, and m is greater than n, m is greater than n. Okay. So, what that means is, this implies that number of equations is greater than number of unknowns, and which also implies that this is basically an over determined system, because number of equations is greater than this is basically an over determined system. Now of course over determined system, frequently this has no solution, frequently no solution exists unless the vector y bar belongs to the column space of A. So frequently, typically, because of the noise in this system, typically does not exist. For instance, you can take a simple example. Let us take m equal to 3. What we have is, we have y1 equals a11. So A equals 3 cross 2 matrix. So we have y1 equals a11 x1 plus a12 x2, y2 equals a21 x1 plus a22 x2, y3 equals a31 x1 plus a32 x2. Now you can see these three represent 3 lines. So what happens when you plot these things? You have 3 lines. So you basically have 3 lines, each represents a line. Okay. Now the solution, now unless all the lines intersect, no, there is no solution unless all the lines intersect at a common point. Alright. So you see this point. So you have 3 lines, that is 3 equations, 2 unknowns. Okay. So there is no solution unless all the lines intersect at a there is no solution unless all the lines intersect at a single point. Alright. So you have 3 equations basically, 2 unknowns, and frequently if you take 3 lines at random, then they will naturally not intersect. It is highly unlikely that they all intersect at a single point, which means there will be no solution. So in such a scenario, you will have to find an approximate solution, or what I mean by that is some solution that best fits the model, okay, or best explains the observed vector y. This is also known as the maximum likelihood vector x. Okay. So it is interesting. So typically, and this is because this happens because of the noise in the model. Typically what happens is, you have y bar equals ax bar plus n bar. Okay. So this is, what is this? This is your model noise. And what happens because of this model noise? This means your y bar is not equal to ax bar, which means if you form y bar minus ax bar, there for any x bar there is always, because there is no solution, for any x bar there is always an error. This is basically your model error or your approximation error vector. So you can also call this as the error vector, which is basically the approximation error. This is basically the approximation error, and to find x bar you have to find best x bar, that is which best explains y bar. What you do is minimize the approximation error. Now error is of course a vector. What does it mean to minimize the error? We will simply minimize the norm of this error vector. So we will minimize the norm of the error vector, which is basically equal to minimizing norm of y bar minus a x bar, which is basically equivalent to minimizing norm square of y bar minus a x bar square. Okay. And this problem where you are minimizing, and this is the 2 norm square, the L2 norm, and when you are minimizing the norm square, so this is the vector x bar which gives you the least squared error norm. So this is known as the least square solution. This is known as the least square solution, or this is known as the least squares problem in fact. This is known as the least squares problem, and this is very popular in communications. This arises when we are going to explicitly show some examples. So this arises very frequently in communication and signal processing applications. Okay, so this arises very frequently in communication and signal. And in fact, if you look at this, this is nothing but this is a quadratic objective function. So this is also termed as a quadratic program. So this minimize norm of y bar minus a x bar square, this is termed as a quadratic objective function. It is termed as a quadratic program, or basically a QP. Okay. And finding the solution of this QP gives the best estimate of it. This is also known as the maximum likelihood estimate. So the solution of this gives the least squares problem, gives the maximum likelihood estimate. In fact, strictly speaking, the maximum likelihood estimate in Gaussian noise. Okay, so this gives the what is termed as the or basically if one asks the question what is the vector x bar which has the maximum likelihood, right, which best explains the y, which has the maximum likelihood of having occurred, that is the vector x bar which basically minimizes the least squares, this which is the solution to the least squares problem, that is it minimizes the square, or it gives the least squared error, least squared norm of the error vector. Okay. And this can be solved as follows, and it is not very complicated. So what we do is that to find the solution, so we want to find the least square solution. And that can be found as follows. We want to minimize norm y bar minus a x bar square. So what we do is basically, remember, norm square of a vector, this is nothing but vector transpose times itself. So this is y minus a x bar transpose times y bar minus a x bar, which is equal to y bar minus x bar transpose a transpose into y bar minus a x bar, which is equal to y bar transpose y bar minus x bar transpose a transpose y bar minus, now this has to be transpose, minus y bar transpose a x bar plus x bar transpose A into x bar. Now, if you can look at this, these two quantities are the same, these are the transpose of each other and scalar quantities, x bar transpose A transpose y bar transpose A x bar. So, you can take the twice of one of these. So, this will be finally simplified as y bar transpose y bar minus twice x bar transpose A x bar transpose A y bar plus x bar transpose A x bar. And now, if you call this as now this is an objective function, because here you have no constraint, you have only the objective function as x bar. So, you take the gradient of f with respect to x bar, and now you can see y bar transpose y bar, gradient of that with respect to x is 0 minus twice x bar transpose A transpose, you can treat this as x bar transpose c bar. So, the gradient is simply c bar. So, minus twice A transpose y bar plus x bar transpose A transpose x bar, that is you can treat this as x bar, you can treat this as matrix P, which is positive semi definite, x bar transpose P x bar. So, the gradient is twice P x bar or twice A transpose A y bar. Now, you set this equal to 0 to find the optimal value. So, you set gradient equal to 0 to find optimal value. This implies, now if you set this equal to 0, what you, now these 2's cancel, okay, you cancel the 2. So, what you get is A transpose A y bar equals A transpose A, this has to be A transpose x bar. So, you have A transpose A x bar equals A transpose y bar, and what this implies is basically you have x bar, or you can call it x hat, typically it is used in the context of estimation. The optimal value of x is x hat equal to A transpose A inverse into A transpose y, assuming A transpose A to be inverted, because you can see A transpose A will always be a square matrix, correct, because A is m cross n and A transpose is n cross m. So, A transpose A will be n cross n matrix, I am sorry, this is A transpose A will be n cross n, A transpose A inverse will also be n cross n. So, this is the least square solution, assuming A transpose A is invertible. It is a very compact and elegant form. Least squares problem is also termed as the LS, and this assumes that A transpose A is invertible. This assumes A transpose A to be invertible. So, that basically gives us the least square solution, and in fact, this is one of the most fundamental problems in signal processing, and also for that matter in estimation and communication, and so arises so frequently. Its solution is very well known, and it is taught in a lot of courses, and in fact, this analysis of this problem forms one of the staples of several courses, all right. And I think this is one of the most important optimization problems with various applications that we are going to encounter in this course. So, we will stop here and continue in other modules. Thank you very much.